Hello everyone, in this video we'll be talking about variance of a random variable. Now when we have a random variable that takes different values with different probabilities, we may not be just interested in the expectation. We may also be interested in what is the spread of this random variable. For example, let us assume that there are multiple students in a class who are submitting or who have gotten grades for a particular homework. Now as an instructor, what the instructor would be interested in is what is the spread of the grade points for this particular homework. For example, if everybody got the same grade point, then the variation is 0. In comparison, if there is a high variation, then we know that many students got grade points very different from the average grade point in the class. Formally, we measured this variation using variance of a random variable x. Now, variance of a random variable is defined as follows. We take x minus expectation of x. We take the square of that. Now as x is a random variable, x minus expectation of x whole square will also be a random variable. We take the expectation of that. Now if you remember, expectation of x is also sometimes represented by mu, so this particular formula can be simply expressed as expectation of x minus mu whole square. Now the standard deviation of x is basically the square root of this variance. Sometimes it might be easier to think of the standard deviation rather than the variance because it's the same scale as the random variable itself. So kind of it gives you the deviation that you can apply across the expectation. Now just to make this point clear, let us assume that the grade point average in a class is 20 out of 30 with a standard deviation of 5 grade points. Then what this roughly means is that most of the students have grade points within the range 20 minus 5, which is 15, and 20 plus 5, which is 25. That is, most students write roughly in this range. Just a note, this may not always hold true. It depends on the characteristics and the distribution of the random variable, but this is a good way to think about standard deviation and variance. Okay, so next let's look at how we compute this variance. In the previous slide and in this slide as well, what I've stated here is the expression for the variance of a random variable x, which is expectation of x minus mu whole square. Now to calculate the expectation of x minus mu whole square, what we do is we have small x minus mu whole square, where small x is the value that the random variable capital X can take, and we multiply that with probability that the random variable takes that value x, and then we sum it over all the different values of x. Now the important thing that you have to remember is that expectation does not depend on the particular value of x, of small x, that the random variable capital X can take. Expectation is a number and it's a constant. It only depends on the probability mass function of capital X. What we can do is we can simplify this formula for variance of x, and what you actually get is expectation of x square minus mu square, where mu square is nothing but expectation of x whole square. So you can simplify this into this particular formula. And in this particular video, what we are going to see is how we actually derive this particular formula. Okay, so let's see how we can get this formula for the variance of x. So it's nothing but a little bit of algebra. So we start off with the formula for variance of x. And what we do is we just expand x minus mu whole square. Now x minus mu whole square is nothing but x squared plus mu square minus 2x mu. And what we do is we then expand this. Now when we expand this, this one summation becomes 3 summations. What we are doing is we are multiplying probability of x, capital X, equal to the small x with each of those individual terms which we saw in the parentheses. So the first term is going to be x squared, probability of capital X equals to small x, summation over x. The next term is mu squared, probability of capital X equal to small x. Once again, the summation is over x. And the third term is minus 2 x mu, probability of x equals x. The summation is again over small x. Now the interesting thing to note here is the first term, which is x squared, probability of x equals x. That is nothing but expectation of the random variable x squared. Now for the second term, what we can see is mu squared is nothing but a constant. It's expectation of x. And as I just mentioned in the previous slide, expectation of x is just a constant. So mu can just come out of the summation. Now what we have in the summation is we are summing over probability of x equal to x for all values of x. So this summation is going to evaluate to 1. So hence the second term, which is mu square probability of capital X equal to small x, is going to evaluate to mu square. Now for the third expression, which is minus 2 summation x mu probability of capital X equal to small x, what we can do is we can once again take the mu out of the summation because it's a constant. And what we are left with is x probability of capital X equal to small x, and a summation over that. If you recall, this is nothing but the expectation of x. And expectation of x is nothing but mu square. So the second term evaluates to mu square, and the third term evaluates to minus 2 mu square. Hence, what we are left with is minus mu square. Hence, the first particular term, as I mentioned, is going to be expectation of x square. And the second and third terms together will evaluate to minus mu square. And hence, we have this particular expression, which is the variance of the random variable. So this is the derivation for why variance of x evaluates to expectation of x squared minus mu square, where mu square is nothing but expectation of x, the whole thing raised to square. I hope this video helps you understand how we get this particular formula for the variance and what the variance for random variable actually captures. If you like this video, do subscribe to my channel and watch the rest of the videos in the playlist as well. Thank you for watching.